All right. I hope you had a really restful Easter weekend. I mean, as good as it could possibly be. We're coming back to Chem 20. We're going to continue on with acids and bases. So, we've seen some things about acids and bases already. For example, we've seen that acids, they have a pH of less than 7. We're going to see what pH actually means today. We saw that they ionize, they don't dissociate, they release H plus ions when they do ionize, and we'll see those H pluses. Remember, they can react with a molecule of water and form a special chemical species called a hydronium ion. We'll do one of those just to get us back up to speed. And we also saw that acids are electrolytes. In other words, when they're in solution, they conduct electricity. So let's do an acid here. Let's just do the most, I almost said the most basic. I meant the most like regular acid we could think of, which is HCl, hydrochloric. That's also the strongest acid. So when HCl is added to water, HCl itself is actually a gas. But it really, really likes to grab onto water molecules. When it does, the first step in our little equation is it ionizes. It breaks into H pluses, and what's left? Cl minus, a chloride ion. Boom. So this is the first step. Now the thing is, this H plus is special. When you make an H plus in water, and I'll put bracket AQ, it will react with that water molecule. So here's my little H2O bracket liquid, and it's going to form this interesting little ion, H3O plus, and that is our hydronium ion. The net, in other words, the total amount of stuff going on. If I look in these two equations, I can call this equation 1, equation 2. If I look for things that are the same on both sides of the equation, the only thing that is identical is the H plus. So what do I have on the left side of the arrow? In other words, the reactant side. I've got HCl, and I have H2O. And that's bracket L, and I'll just say that's bracket G. It doesn't have to be bracket G, but for this example we might as well. And what does it make? It makes an H3O plus. That's our hydronium ion. And it makes our chloride, or Cl minus, ion. So I wrote two equations down, and I crossed out what was the same on both sides. Math people, you're going to see this and be like, hey, hold the phone. This is exactly what we do in Math 10C when we do systems of equations. That's exactly right. We've just taken two chem equations instead of math equations, and we've removed the thing that is the same on both sides. So these skills that you learn are kind of transferable. They're not just good for one thing. And the real, like, the students who really get it are the ones who can see a procedure or a technique or a skill in one class and say, hold up, this is what we did in a different class, or hey, isn't this similar to the idea in this other class? And so I like to kind of make sure that you guys, or I like to point these out to you. So what about bases? We said that the base has a pH bigger than 7. I'm going to put this in quotes though. So far we've said that bases dissociate because our understanding of bases so far is that they are all ionic compounds that contain hydroxide. Now this is not strictly true. In another video we're going to talk about other chemicals that are still bases, but they don't release an OH. Not from them. Turns out that if you form an OH, you're a base. It's an interesting distinction. We'll get into it in a bit. And obviously, our bases are electrolytes. Remember, that means that when we dissolve them in water, they allow for the flow of electricity. So let's do a very quick base reaction. And let's use the standard, most regular base. That's our boy, sodium hydroxide. We see it all the time. We're going to add it to some water. To a liquid. And we're going to get a dissociation equation. You guys remember these. So that means that the chemical falls apart into the ions that it was composed of. So Na plus aqueous, OH minus aqueous. Now here's the point of this lesson, because this was all review. Now we're going to get into the actual meat. There's got to be a way to figure out how much H3O or how much OH minus there is in a solution. And amazingly, it's connected to the pH. Now, if we actually got a moles per liter amount of OH or a moles per liter amount of H3O, that is the reality. That's how much H3O is in the solution or how much OH is in the solution. How do we get numbers like pH? How do we say, why is pH for an acid below 7? Why is the pH of a base above 7? Let's talk about that now. The most important thing is when there's a lot of H plus in a solution, it means there's not very much OH minus. If there's lots of OH minus, there's not very much H plus. If you think about what we know about acids and bases, this is going to make sense. So if we've got H pluses in a solution and we've got OH minuses in a solution, and I'll put my little states down here. Everything is going to be aqueous on this side. If I have one of these and one of these, oh hey look, we get an H2O liquid. So if you have two of these and only one of these, you use one of them to make a water. That's a neutralization reaction. But then you got another H plus kicking around. This is why when there's lots of H plus, there's like no or hardly any OH minus. And when there's lots of OH, there's hardly any H plus. It's because if you ever have an H plus and an OH minus in the same place, they're going to want to neutralize and form a molecule of water. So let's talk about pH. It's related to the amount of H3O. In other words, how many H pluses are in our solution. And the math, or the formula, uses something that most folks unfortunately don't run into until Math 30-1 or Math 30-2. And that is the log. Logs, just for a little bit of information, logs are a way of taking numbers that have very, very big exponents or very, very tiny exponents and making sense of them, so you can graph them in a more meaningful way. So pH is negative log and then the concentration of H3O. And if we want to go backwards, oops, let me just put a little plus there. If you want to go backwards, and this is not something that you would mathematically have to do in Chem 20 as far as like figuring out how to manipulate this formula, absolutely not. You don't have to do that in Chem 20 because you guys don't have the knowledge of how logs work. But they are related to or part of the way that we express exponential numbers, big numbers or tiny numbers. So our H3O concentration is literally just going to be 10 to the exponent of negative pH. So going from one to the other is simply a matter of plugging it into your calculator. The one thing that I want you to be cautioned about is that the number of sig digs in your H3O plus is the number of decimals in your pH. So that's quite simple, but it's an important rule. So let's do a quick example. Something like this. The hydronium ion concentration of a solution is 6.33 times 10 to the minus 4. What's the pH? Okay, so we go back to our formula. Very simple. pH equals negative then the log button on your calculator, which is on the left-hand side. It's beside the 7. We have H3O. So I'm going to throw my numbers in. So I have pH of my solution equals negative log, and then the H3O concentration, 6.33 times 10 to the power of minus 4. And that's in moles per liter. Concentrations, remember, in chemistry are shown in moles per liter. So I just have to get my calculator out. Negative log 6.33 times 10 to the minus 4. And I get a number with a lot of decimals. It's not round at all. We have 3.19859.629. Not a clean number, but remember, since we have 3 sig digs in our H3O concentration, that means we will have 3 digits in the decimal places. So it's the decimal places again that matter. So it'll be 3 point. Now I look at the decimal places here, 198. I have to check to see if I round that up or down. So I look to the next number, and that is a 5. That means that I must round this 8 up to 9. So the pH of this solution is 3.199. And this doesn't have a unit. In other words, you don't say like 3.199 pHs or pHs per liter. No, it's just the pH is this number. It has no unit attached to it. So you guys can feel great about the fact that finally there's no unit that you need to write down. Let's try going backwards. So what's the hydronium ion concentration in a solution of pH 8.3? So that's on the basic side of things. That means that we should see a very, very small number for pH. In fact, whenever the pH goes down or up by 1, it represents a change multiplying or dividing by 10. That's why we use log, because logs express a change in multiples of 10. What that means is the difference between an acid that has a pH of 2 and an acid that is a pH of 3, there are 10 times more H3Os in the acid of pH 2 compared to the acid of pH 3. So let's go in with our little formula. So H3O concentration equals 10 to the power of negative pH. So our H3O concentration in this example is 10 to the, oops, I shouldn't use the add exponent thing. I don't know why I started doing that. That's kind of silly. 10 to the power of negative 8.3. So I just have to throw it into my calculator. 10 hat negative 8.3. And we only have one sig dig here, or sorry, one decimal place. which means we get one significant digit in the answer. So our number is 5.0118, and I'll fix the number in a sec, and that's times 10 to the minus 9, and since it is a concentration, we measure that guy in moles per liter. So this would be, since we only get one sig dig, one decimal in the pH, 1 sig dig, so we quite simply have 5 times 10 to the minus 9 moles per liter. And then we're good. So remember that rule. The number of sig digs in the concentration is the number of decimals in the pH. One thing that students have trouble with, and this is going to pop up as well in Chem 30, when you move on to Chem 30, I'm going to say this. An acid's concentration is not always its H3O concentration. It's only true in a strong acid. That's the only situation that will, if you make a solution of 0.2 moles per liter H3 or of HCl, you will have 0.2 moles per liter of H3O. And the reason why has to do with the strength of the acids. The only strong acids that we talk about in, well, the only strong acids are these: HCl, HNO3, and H2SO4. That's our buddy sulfuric. They're the only three acids where this is true. What does that mean? It means if you, I don't know, for example, if you dissolve 1 mole of HCl in a liter of water, you get a 1 mole per liter H3O concentration. If you take 1 mole of a weak acid, like acetic, that's the acid in vinegar. If you measure out 1 mole of acetic acid and you put it into a liter of water, yes, you have a 1 mole per liter acid solution, but the problem is not all of the H's in the acid fall off. That means that the H3O concentration is less. That's why you can safely touch vinegar from the store. It doesn't corrode your skin or hurt you. But if you had a similar concentration of sulfuric acid or hydrochloric acid, you would not want to touch that stuff. It would be harmful. So the concentration of the acid is the same, but the concentration of the H3O is much different. There's way more H3O in a strong acid than there is in a weak acid. So let's talk about pOH. Now pOH is the exact same idea as pH, except instead of us caring about the H plus amount in a solution, we care about the H3O, or sorry, oops, the OH concentration of the solution. So pOH is negative log OH minus. And that means the flip side of it is, if you want to know how much OH is in a solution, that's going to be equal to 10 to the power of negative pOH. So let's do a quick example. So the hydroxide concentration, that's what we care about with pOH. It literally says OH there, so we know we're talking hydroxide. So the hydroxide concentration of a solution is that, what is the pOH? Piece of absolute cake. So our formula there, so negative log, and now we write down the OH concentration, 2.73 times 10 to the minus 4 moles per liter. I throw that into my calculator, negative log 2.73 negative 4, and we get 3.56. Remember, the number of sig digs here gives us the number of decimal places, and it's the same for pOH. So this will be 3.564. And to go backwards, OH minus. So a solution of drain cleaner has a pOH of 2.68. What is the OH amount? So same idea. We're going to go 10 to the power of negative pOH, 2.68. That's our OH concentration. So we plug and we chug, so 10 to the power of negative 2.68. And this is a goofy number, it's not very big. It's actually bigger than some of the other numbers we've played with today. So 002, 089. We're going to have to turn this bad boy into scientific notation. We have 2 decimals here. That means we get 2 sig digs in our answer. So there's my first sig dig. There's my second sig dig. So in order to go to scientific notation, we put down our 2. We put down a decimal. I look at the 0 and I look beside it. I have to round up. So from 2.08, I must round up to 2.1. Now we find out what our exponent for scientific notation is. So 2.1 times 10 to the minus 1, 2, 3. And that's in moles per liter. So again, pH and pOH are related concepts. pH monitors, or is a way of expressing how much H3O, there is in a solution, and pOH is a way of measuring how much OH there is in a solution. And one last thing, just because people always kind of mess this up. A base has a high pH, but a low pOH. An acid has a low pH and a high pOH. Higher numbers on these scales means there's less of that thing. That's what confuses students. When you're like, oh, this chemical has a pH of 11, that means it has 1 times 10 to the minus 11 hydronium ions. 1 times 10 to the 11, minus 11 rather, is an insanely tiny amount. So the bigger the pH number, the less hydrogen you have. The bigger the pOH number, the less hydroxide you have. So when the number goes up, the less of that thing you have. So I hope that clarifies some things.